Hello and welcome to another one of our online lecture videos for Math 122. Here we're going to get a chance to start Chapter 12. We're going to take a look at discrete random variables. And here we're going to be talking about expected value, variance, and standard deviation. And I got some formulas for you. The expected value, we call this capital E of x for expected value. And this is given by a sub 1 times p sub 1 plus a sub 2 times p sub 2 plus next would be a sub 3 times p sub 3 plus so on and so forth plus a sub n times p sub n. Where each of the a values, we say where each a sub I represents a possible outcome of an event, and each p sub I, all of the p values, represent the probability that that specific event will occur. So a sub 1 is outcome number 1, and p sub 1 is the probability that that outcome occurs. A sub 2 is outcome number 2, p sub 2 is the probability that that outcome occurs, and so on and so forth. And that's how we find the expected value. Think of the expected value like an average, or sometimes we call it the mean. Let's talk about variance next. So our formula for variance, we have what we call it var of x, var for variance. This is a sub 1 minus m in parentheses squared times p sub 1 plus a sub 2 minus m in parentheses squared times p sub 2 plus so on and so forth. The last term is going to be a sub n minus m in parentheses, we square it, times p sub n. Where here a refers to the outcomes again, p refers to the respective probabilities, but m is the expected value. So what am I doing here? I'm taking an outcome, I'm subtracting away the expected value, I'm squaring that difference, and then I'm multiplying by the probability that that specific outcome occurs. And I'm doing that for all of the outcomes, and then we're adding them all together. Then, as soon as we found the variance, we can actually find the standard deviation pretty nicely. The standard deviation is just the square root of the variance. So once we have the variance, standard deviation is actually the quickest to find. Let's take a look at a first example. Here we have a probability table, and I want to compute the expected value, the variance, and the standard deviation of my discrete random variable x using the following table. And here I have the different outcomes and their respective probabilities. The outcomes are 1, 2, and 3, and the corresponding probabilities are 1/3, 1/6, and 1/2. Now this means that the likelihood that outcome 1 happens is a 1/3 likelihood. The outcome 2 occurs with probability 1/6. And the likelihood that outcome 3 occurs, well, that is probability 1/2. Something that we can do to check to make sure that our probability table is correct is by adding up all of the probabilities. So if I add these together, 1/3 plus 1/6 plus 1/2, we sort of notice something about this. Well, first of all, we notice we need a common denominator. I'd multiply 1/3 by 2/2, that gives me 2/6, plus 1/6, plus we would multiply 1/2 by 3/3, gives me 3/6. And if I add these all together, 2 plus 1 plus 3 gives me 6/6, gives me 1, which is what I'm looking for. I want to make sure that all of my probabilities sum to give me 1. Think of that sort of like 100%. That means I haven't left anything out. It means I have all of the different outcomes here. But that's just a way we could check to make sure our probability table is correct. Now, if I want to find the expected value, E of x, we use our formula from before. Basically, that means take an outcome, multiply it by its probability, and add that for all of the different possibilities. So I take outcome 1, multiply by its probability 1/3. Take outcome 2, multiply by its probability 1/6. And I take outcome 3, multiply it by its probability 1/2. Now what does this give me? Well, we can go ahead and compute. 1 times 1/3 gives me 1/3. 2 times 1/6 gives me 2/6. And 3 times 1/2 gives me 3/2. And then from here, I can go ahead and get a common denominator. I could reduce 2/6, but I'm going to need a common denominator anyways, it looks like. So I would go to 1/3 and multiply by 2/2. That gives me 2/6. Plus The next one, 2 over 6, I didn't reduce it, so it already has the common denominator. And then for 3 over 2, I multiply by 3 over 3, and that's going to give me 9 over 6. And then we add these all together. So 9 plus 2 plus 2, that gives me 13 divided by 6, which is my expected value. So we'd say, okay, our expected value, I'll write it over here, expected value E of x is 13 divided by 6. Now we're ready to find the variance. And remember, variance has sort of a bit more of a complicated formula. What I want to do is I want to take the first outcome, which is 1. I want to subtract away the expected value. So 1 minus 13 over 6. And then I want to square that difference. And then I want to multiply by its probability, which was 1/3. And I have to do this for all of the sets of information. So next, I would take the next outcome 2, subtract away expected value 13 over 6. I want to square that difference, and then multiply by its probability, which was 1 over 6. And then for the last possibility, I take outcome 3, subtract away the expected value, 13 over 6. I got to square that difference, and then I multiply by the probability that outcome 3 occurs, which was 1/2. Now there's a lot of arithmetic for me to do here. So what I need to do is get some common denominators, do the subtraction, do the squaring, do the multiplying, you name it. So here for this first value 1, well, I'm going to write that as 6 over 6. Minus 13 over 6, I want to square it, multiply by 1/3. 2, if I get a common denominator, that's 12 over 6. Minus 13 over 6, I want to square that difference and multiply by 1 over 6. And then 3, if I get a common denominator, that's 18 over 6 minus 13 over 6. I want to square that difference and multiply by 1/2. Now, if I do the subtraction, here 6 minus 13 gives me negative 7 over 6. I got to square it and multiply by 1/3. 12 minus 13 gives me negative 1 over 6. I want to square it and multiply by 1/6. And 18 minus 13 gives me 5 over 6. I want to square it and multiply by 1/2. And now I can go ahead and square. Negative 7 over 6 times negative 7 over 6 gives me 49 over 36 times 1/3 plus negative 1 over 6, if I square it, gives me positive 1 over 36 times 1 over 6. And then plus 5 over 6, if I square that, gives me 25 over 36, and then times this 1/2. Now, I could go ahead and multiply everything out, but I want you to notice that I'm going to need a common denominator, and I'm not going to get a common denominator right then. But think about how the denominators look. I have 36 times 3, I have 36 times 6, and I have 36 times 2. The common denominator is going to be 36 times 6, or what is that, 216, right? So what I can do is I can go here to the first thing before multiplying it. I want to get that common denominator, so I would multiply that by 2 over 2, which is just the number 1, so it's a safe move to make. I haven't really changed it, just going to modify it a bit. And this last set of fractions, I have 36 times 2 in the bottom. Well, I'd have to multiply that by a 3 over 3. Now, all of these denominators are 36 times 6. 36 times 6, which means that I can write these all as like fractions. So here, I can go ahead and combine all of them into one fraction. I have 49 times 1 times 2, that's 49 times 2, plus 1 times 1 is 1, plus 25 times 1 times 3, that's 25 times 3. And this is all divided by my common denominator, 36 times 6. And then here we can go ahead and work through the rest of this. 49 times 2, what is that? 98 plus 1 plus 25 times 3, you got 3/4, you got 75 cents, so that's 75. Divided by 36 times 6, we said that is 216. Then here I can go ahead and add in the numerator. So 98 plus 1, that's 99, plus 75 gives me 174. divided by 216. And I can actually reduce this. I can reduce the top and the bottom by 6. Now 6 goes into 216 36 times, and 6 goes into 174 29 times. So my variance reduced as a fraction, and certainly that TI-30X2S calculator would help here, but if I'm doing it by hand, I get for the variance, I get fraction 29 divided by 36. Now with a little bit of space here that I have left over, I can now find the standard deviation. The standard deviation is just, I abbreviate this SD for standard deviation, it's the square root of the variance. So this is the square root of 29 divided by 36, which I can use the quotient property of the radical to simplify this, say square root of 29 divided by square root of 36. Because the square root of 36 is going to be a nice number, right? Square root of 36 is 6. So my standard deviation is radical 29 divided by 6. And this is just the square root of the variance. So we got them all, right? Expected value was 13 over 6. Variance was 29 over 36. And standard deviation simplified to radical 29 divided by 6. Let's take a look at this next set of examples. Here I have 3 different probability tables, and for each of these I want to find expected value, I want to find variance. We'll talk about standard deviation as well, because why not? And I want to compare them for the different tables. Let's start with this first table. Here for the expected value, I would want to take the outcome and multiply by its probability, and then add those products together. So we got outcome 4 times its probability 1/2, plus outcome 6 times its probability 1/2. We say, okay, 4 times 1/2 is 2, 6 times 1/2 is 3, and then 2 plus 3 gives me 5 for the expected value. Now that I have the expected value, I can find the variance. So here for the variance, remember I would take the outcome 4, subtract away expected value 5, square that difference, and then multiply by probability 1/2. Then I would take the next outcome, which was 6, subtract away expected value 5, square that difference, and then multiply by probability 1/2. So what does this give us? 4 minus 5 gives me -1. We square it and multiply by 1/2. 6 minus 5 gives me +1. We square that and multiply by 1/2. Now -1, if I square it, gives me +1. So we have 1 times 1/2. And 1 squared gives me 1, so we have 1 times 1/2. So that's 1/2 plus 1/2 gives me 1 for the variance. We'll go back, we'll find the standard deviations at the end, just for fun. Let's move on to the next probability table, but we'll find the expected value and the variance of this. So here I have outcomes 3 and 7, each with probability 1/2. I go and find the expected value, I would take outcome 3, multiply by its probability 1/2, take outcome 7, multiply by its probability 1/2, and these don't reduce nicely, so I'll just keep them as fractions. We have 3 over 2 plus 7 over 2. Adding them gives me 10 over 2, which gives me 5 for the expected value. Should seem maybe familiar, right? Well, let's go ahead and find the variance and see what that looks like. So I would take outcome 3, subtract away expected value 5, square that difference, and multiply by 1/2. Then I would take outcome 7, subtract away expected value 5, square that difference, and multiply by 1/2. And what's that going to look like? Well, 3 minus 5 gives me -2. I want to square it and multiply by 1/2. And 7 minus 5 gives me +2. I want to square that and multiply by 1/2. Now, -2, if I square it, gives me +4 times 1/2. And 2, if I square it, gives me +4 times 1/2. We say, okay, 4 times 1/2 is 2, so I get 2 plus 2 gives me 4 for the variance. So here my variance is 4. We got one more probability table to look at, and then we'll talk about what we're noticing and have a bit of a discussion here. Now I have outcomes 1 and 9, each happening with probability 1/2, let's find the expected value. So I would take outcome 1, multiply by its probability 1/2. I would take outcome 9, multiply by its probability 1/2. And these don't reduce, so I would leave them as fractions. 1 times 1/2 is 1/2. 9 times 1/2 is 9/2. 1/2 plus 9/2 gives me 10/2, which gives me 5 again. Some conspiracy, right? Must be. Let's take a look at the variance. I take outcome 1, subtract away expected value 5, square that difference, and then multiply by probability 1/2. Add to this, now I'm going to take outcome 9, subtract away expected value 5, square that difference, and multiply by 1/2. If I go through the arithmetic here, 1 minus 5 gives me -4. I still got to square it and multiply by 1/2. 9 minus 5 gives me +4, and I want to square that and multiply by 1/2. Now, -4, if I square it, gives me +16 times 1/2. Plus 4, if I square it, gives me 16 as well, times 1/2. We say, okay, 16 times 1/2 gives me 8, plus 8, and 8 plus 8 gives me 16 for the variance. Now let's talk a bit about what we're discovering here. We will still talk about standard deviation, but let's say what we've all been noticing. For each of these tables, the expected value was the same. Expected value was 5 for all 3 of these tables, which means that the average is 5. And sort of think about it in context, it makes sense, right? If I had, let's say, 2 quizzes in chemistry, and my quiz grades were a 4 and a 6 out of 10, then my average was a 5, right, out of 10. Or if those same sort of quizzes, if let's say my scores were a 3 out of 10 and a 7 out of 10, well, then the average is still a 5, right? 50%. Or if I did really good on one and really bad on another, if I had a 1 out of 10 and a 9 out of 10, still my average is a 5, right? 5 out of 10. But I want you to notice that the variance is incredibly different. For the first table, the variance is 1. For the second table, the variance is 4. And for the third table, the variance was 16. And those are wildly different, while the expected value was the same. Here's what I want to mention about this. The expected value, E of x, is a measurement of central tendency. Which really tries to tell me where the middle would be of my set of data. It's an average, so it's trying to find what's right in the middle. And certainly it's true, halfway between 4 and 6 is 5, halfway between 3 and 7 is 5, and halfway between 1 and 9 is 5 as well. And that's because all of the probabilities are the same. It's 1/2 for all the probabilities in the probability table. So everything's equally weighted. The variance, however, doesn't talk about the center of our data. The variance talks about the spread of our data, how far apart it's spread. And the standard deviation, which is just the square root of the variance, also talks about the spread of the data as well. In this case, I think the standard deviation is actually the most telling, so let's find it. For the first table, the standard deviation would be square root of 1, which is 1. So we have standard deviation is 1. For the second table of information, the standard deviation would be square root of variance, which is square root of 4, which gives me 2. And for the third table, the standard deviation, which is the square root of the variance, would be square root of 16, which gives me 4. Standard deviation just sort of corrects the variance, because for the variance, we're doing a lot of squaring. So taking the square root sort of cuts it back down to size, but also talks about the spread of the data. And in this case, what the standard deviation, and the variance is trying to tell me this too, but the standard deviation does a better job of telling me. The standard deviation is trying to tell me how far away my data is from the expected value. So for example, 4 and 6 had expected value 5, but they're each 1 away. So standard deviation was 1. 3 and 7 in that table had expected value 5, But how far away are 3 and 7 from 5? They're both 2 units away in either direction, so the standard deviation was 2. And lastly, we had 1 and 9 in our probability table. The expected value is 5, right in the middle, but these are far away from the middle. In fact, 1 and 9 are both 4 units away on either side from 5. So the standard deviation we saw was 4. This is just to sort of talk about what these things tell me. The expected value gives me a measurement of central tendency. Where is the center of my data? The variance and the standard deviation both tell me about the spread of the data, how far away my data values are from that measurement of central tendency. Really fun to talk about. I'm a huge fan of probability and statistics in general. So you could get me talking about this stuff all day, but I know you're very busy. So if you want to talk more about this, send me a message on Piazza. I love talking about this stuff. But let's move on to our next example. A little bit more cheery, we have the number of accidents per week at a busy intersection was recorded for a year. There were 11 weeks with no accidents, 26 weeks with 1 accident, 13 weeks with 2 accidents, and 2 weeks with 3 accidents. A week is selected at random and the number of accidents is noted. We want to let X be the outcome. We'd like to write out the probability table for our discrete variable X, compute the expected value, and interpret it in context of our word problem. Now, hopefully you're lobbying for some safety organization and you're not just sitting there at the intersection recording the number of accidents that happen per week. But nevertheless, you have this information. Let's organize it into a probability table. We need to organize. So let's go ahead and take a look at the information that we have here. What are the different sort of outcomes? The outcomes really refer to the accidents. And what are the possibilities there? I had 11 weeks with no accidents, so that's 0 accidents, which is good. 26 weeks with 1 accident, so 1 accident is another outcome. 13 weeks with 2 accidents, so 2. And 2 weeks with 3 accidents, so 3 accidents. So the different outcomes are 0, 1, 2, or 3 accidents on any given week. The probability column sort of talks a bit about frequency. Right? We said there were 11 weeks with no accidents, so I'll put an 11 here. 26 weeks with 1 accident, so I'll put a 26 here. 13 weeks with 2 accidents, so I'll put a 13 here. And then 2 weeks with 3 accidents, so I'll put a 2 here in that bottom row. But are these probabilities? No, they're not quite right. Probabilities have to be somewhere between 0 and 1. They should be proper fractions. So what I have now is actually referred to as frequency. How can I make these into probabilities? What should I do? I want to divide by 52 for each of these. Why 52? Well, we said we recorded for an entire year. And if you know, we have 52 weeks in a year. But if we didn't know that, let's say we weren't, comfortable with the idea that, hey, we got 52 weeks in a year. Some of us know it. Some of us don't even really think about it. Because what do? We just do what we do anyways. It doesn't matter how many weeks there are in a year. I'm gonna have to deal with every week when it shows up, right? Am I right? Am I right? Yeah. Well, if I didn't know that, I could figure it out by just adding up the numerators, because I would want this to add up to 1 for the probabilities. So, and we could go ahead and say, okay, well, if there were 11 weeks, and then 26 weeks, and then 13 weeks, and then 2 weeks that I had all these data for, well, we'd add them all up, and that would give me 52. And I say, okay, all right, so then makes sense, right? 52 weeks in a year. A couple ways to get it. So now we have our probability table filled out. We have the different outcomes, which are the number of accidents that were recorded, and then the probability, which was the frequency divided by the total number of weeks. To make it a bit easier to compute here, I'm actually going to turn these into decimals, just to make the computation a bit nicer for expected value. 52, sort of a weird number to work with, but if you've done a lot of work with decks of cards, if you like to gamble at, Vegas or something like that, then you're probably familiar with how some of these reduce. 26 divided by 52, that's 1/2, or 0.5. 13 divided by 52 is actually 1/4, or 1/4, or that's 0.25. The rest of these, we can get sort of rough approximations for what the decimals would be. 11 divided by 52 is about 0.21. And here, 2 divided by 52, that's about 0.04. And we'd say, well, notice here too, if I add these all up, it's going to give me, 1, like I said it should anyways. 0.5 plus 0.25 is 0.75, so I need 0.25 more. 0.21 plus 0.04 gives me that extra 0.25. But the decimals are just going to be a little bit easier. Now that I have my probability table, I want to find the expected value. Remember, for expected value, I take an outcome and multiply by its probability. So outcome 0 times its probability 0.21 plus outcome 1 times its probability 0.5 plus outcome 2 times its probability 0.25 plus outcome 3 times its probability 0.04. And then here we would go ahead and just, multiply these out. So 0 times 0.21 gives me 0. 1 times 0.5 gives me 0.5. 2 times 1/4, or 2 times 0.25, gives me 0.5 as well. And then 3 times 0.04 is going to give me 0.12, or 0.12 there. We can go ahead and add these together. 0 is not going to do anything, so I'm going to skip over it. 0.5 plus 0.5 gives me 1, plus this 0.12, so this gives me 1.12 for my expected value E of x. And this is good. We found the value mathematically. We are in a math course, so that's the idea. But the question said to compute the expected value and interpret. So I want you to think, well, what does this mean as an interpretation? Remember, think the expected value means sort of like the average. Sometimes we refer to it as the mean, if you've heard that term. So think about what this means in terms of the word problem and the context here. And pause the video, think about it a bit, give it some thought, and then resume the video and we'll talk about it. Hey, welcome back. So let's talk about this. Here with our data, we were recording the number of accidents that happened per week at a busy intersection. We found that expected value to be 1.12. What does that mean in context? Well, we would say the following. We expect, on average, that during any given week, there is 1.12 accidents at this, we'll call it, because they refer to it as the busy, and so we'll say at this busy intersection, but it's an intersection nonetheless. Now, this is definitely a mathematical interpretation. We probably wouldn't say something like this in colloquial conversation unless we were a robot, which I promise I'm not a robot. So we would probably say something like, we expect on average during any given week, there is at least 1 accident at this busy intersection. We found the expected value is 1.12 accidents. I don't know what 0.12 of an accident looks like. Probably just some small fender bender, or you drop your Starbucks on the inside of your car, kind of messes with the interior then. But I'm not really too sure what 0.12 of an accident looks like. But this, of course, is a mathematical computation. So we have to then be willing to interpret it. So we could certainly write it like this, and this is correct. This wouldn't be wrong. No one could, yell at you for this. But this means at any given week, we expect there to be at least 1 accident. Right? Our expected value is actually greater than 1 at 1.12. This gives us an overall picture. It doesn't really tell us about the idiosyncrasies or what was specifically observed, because if we remember from the scenario, there were 11 weeks where there were no accidents at all at this busy intersection. But of the long-standing behavior recorded for an entire year and then averaged out, we say, well, at any given week, we expect there's going to be at least one accident, and actually a little bit more than that at 1.12, which, depending on what we're using this information for, we would use it to perhaps lobby for better safety at this intersection. Maybe there should be a stop sign if there isn't, or, you know, we should reduce the speed limit, something like that. We would use this to then sort of corroborate whatever personal agenda we have. In this case, I'd say, yeah, it kind of looks like from the information that there's a reasonable amount of accidents happening at the intersection. We should do something about it, right? So this is kind of, I wouldn't stand for this if this is my intersection. I'd say, hey, if it's a busy intersection and we're seeing this many accidents, we gotta crack down on something. Am I right? But that's how we would then interpret this as the idea. Expected value is 1.12. That means at random, at any given week, we expect there to be at least one accident happening. So until we can actually do something about it and reduce the statistic, I would say stay away from that intersection, you know. We'll take a look at one last example for the section, sort of a short introduction here. But here our last question says, consider the unit circle. Okay, I mean, I kind of always am. Then the follow-up says, what percentage of points lies within 1/2 unit of the center? Well, what is the unit circle to start? The unit circle is the circle of radius 1. So I want to consider my circle of radius 1. Let me see if I can get a nice sort of circle drawing in here. You probably miss when I would draw the circles by hand, don't you? So there's my circle of radius 1, and I'm going to go ahead and put my grid lines in there. Ooh, well, you probably miss when I would draw the grid lines by hand too. It's still going to be just like kind of okay. It's not going to be perfect, so don't get your hopes up. There's my circle of radius 1, and I want to know how many points lie within 1/2 unit from the center. So I'm going to try to do this sort of by hand. So 1/2 unit away from the center, maybe is about there, maybe about there, roughly. And let's go ahead and let's actually put a circle inside of our circle. How does that sound? That's about as good as I think I'm going to be able to get it. There's my circle of radius 1/2, right? So here we'd say it's 1/2 unit from the center. And I want to know how many points lie inside that middle circle, sort of relative to the outer circle is the idea. And I'd like to know what your sort of first impressions are coming in. And oftentimes, unfortunately, you know, I'm doing this video, you're not here with me, but if we were in class, I would ask you, I would literally ask you this question to your face. I would get up in your face and I would say, hey, what do you think this would be as sort of your first inclination? And a lot of times the response that I get is 50%. And I think that sounds reasonable because we're saying what percentage of points lies within 1/2 unit from the center. The unit circle goes out 1 unit in all directions, and my new circle only goes out 1/2 unit. So I can understand why we would want to say, well, maybe 50%, 50% question mark. But my question is, do you believe that to be the case? Let's find out. The way that I can actually determine this is by using areas. I want to know, okay, inside this circle, 1/2 unit from the center, what percentage of the points lie in there relative to the entire circle outside? And we can find this out by using areas. So we'd say, okay, what's the area of the outer circle? Well, what's the area of a circle in general? Remember, that's pi times r squared. So we'd say the area in general, area A for a circle is pi r squared. And this outer circle is the unit circle. We said the unit circle is the circle of radius 1. So that's pi times 1 squared, which is pi times 1, which is just pi. But what about the area of the inner circle? Well, the inner circle was only half a unit away from the center, so its radius is 1/2. So that's pi times r squared, but here r is 1/2. And if we compute that, well, what's 1/2 if I square it? 1/2 times 1/2 is 1/4. That's pi times 1/4 then, or pi over 4. Now what I want to do to find the percentage of points is to actually divide these. So here I want the area of inside circle divided by area of outside circle. Well, the inside circle, we found that was pi times 1/4 divided by the area of the outside circle, that was pi times 1, or just pi. And if I go ahead and divide these, notice pi cancels. Pi divided by pi cancels. I'm left with 1/4 over 1, which is just 1/4, or as a decimal, that's 0.25. Now I want to make sure that I'm answering the question perfectly. It says, what percentage of points? Now I got 0.25. What would that be as a percentage? That's right, that's 25%. So 1/4 is 25%. So we would say 25% of all of the points lie in this circle that's just 1/2 unit from the center, which if I look at my picture, I think that makes more sense than 50%. My picture is not perfect by any means, right? My circles look just marginally better than they do when I draw them by hand in lecture. But we'd say, okay, it looks like it's definitely not 50%. It's too small, I think, to be half. But I think that's a good starting point for just sort of the way the question is worded, but we can solve it and actually determine what it is. It's 25% of the points. So only 25% of the points are in that inner circle relative to that outer circle, the circle of radius 1, the unit circle. That's it for section 12.1. Let me put the homework in the homework jar. Take a look at the homework on my math lab. And if you have any questions at all about the material in this lecture, if you want to talk more about it, hey, I want to talk more about it too. So send me a message over on Piazza. We can keep this discussion going. But unfortunately, the lecture videos have to end at some point. So that's going to be it for 12.1. We're going to take a look at continuous random variables next in 12.2, and we're going to keep talking about expected value, variance, and standard deviation. But now we're going to bring calculus back into play. I hope you have a great rest of your day. Thank you so much for tuning in, and I will see you next time. Goodbye.